Okay, welcome to this last session of the Hexa-X-II 6G series workshop. And the next presenter will be Liesbet van der Perre, presenting engine-neutral devices versus sustainability goals.
Liesbet, I think you need to unmute yourself once more.
Yes, and I will enter my camera again. Okay. So thank you. And I will be sharing some lessons we learned and also I think some work to do, some research to do to clarify what is the real relationship, the full relationship between energy neutral devices and the sustainable development goals, to in the end use those devices to contribute in a positive way, of course, to the sustainable development goals. And I start with notion of smart dust because this is actually what has been said many years ago. So I'll start a little bit with this vision, explain what we will understand under energy neutral devices. Then I'll talk about the waste aspect because I think when the smart dust vision was launched, people did not think so much about the waste. And then we'll talk about some progress in R&D, but also some work that still needs to be done. So clearly, we have identified that IoT can help to address a number of hard problems like global warming, overhead and noise, mobility problems, ecological problems, and so on, which are often considered also soft themes. So people get stressed by too much noise, and people get stressed and the environment gets stressed by too much cars and so on. So we want to see whether we could connect for a sustainable future and whether IoT can help. And the smart dust vision is actually one that was launched already 10 years ago, I think, stating that sensors or devices could become just a few millimeters in size. That's why they use the word dust, because this would be very small and can share information over wireless networks. And I think the small size was meant to say, well, looks like dust, but now we know that it's not biodegradable as dust typically is. So we should ask ourselves if we go for this smart dust vision where these things could become very small and integrated everywhere, what's their ecological impact and how can we maximize the trade-off between their self-impact and the positive impact they may have on applications? I think one specifically thing we have to check is whether smart dust, if it's not having any battery left anymore, any energy, it will go to sleep and it will become toxic dust instead of smart dust. And there's a prediction, of course, there are many that there will be billions of IoT devices, and this may also end up with billions of batteries that are wasted. And worst case, they are among the dusts. They are somewhere where you don't know where they are, and they are not recuperated and they are toxic. So I think that is the risk we see, that from smart dust we could go to sleeping dust to toxic dust even. And we think that energy neutral devices might be a way to cope with a lot of toxic dust that could end up somewhere, because energy neutral devices could avoid that we have batteries that are wasted. And we have a definition for energy neutral devices that we have agreed upon in the Ambient 6G project that has just kicked off last month, where we say that Ambient 6G says energy neutral means that the devices are powered by ambient energy harvesting or wireless power transfer. These could be either passive or active. Passive devices will use backscattering for uplink communication. Active can themselves also initiate uplink communication. And they could be either battery powered, but then with a rechargeable battery, also reducing the number of wasted batteries, toxic batteries. Or they could be what some people call zero energy, but my colleague in the energy department is furious if I say so. So battery-less devices that use, for example, a supercap, but they always have some energy that they need in order to be able to do something. But so energy neutral in the total sense, you could say, well, the energy is coming in from the environment by harvesting or wireless power transfer, and it can recharge or reactivate or re-energize the device, either in a rechargeable battery or in a capacity, or by the energy being used for bus charactering anyway. There is always a need for energy to communicate, and the idea is that the energy comes from outside, and ideally, theoretically, your device would stay alive forever if we can get this done. So that's how we define the energy neutral devices. Now, to waste or not to waste, that's the question where we came. And in order to understand typical IoT devices, whether it's energy neutral or not, we would need some assessments. And we already know that there could be lots of e-waste, and this is not only the battery. I think that's an important message I want to give in this presentation. It's not just the battery. We need to minimize the e-waste of these devices. And it's the battery, but it's on top of that, it's the electronics, it's other things that are in these devices. And we performed a first life cycle assessment on a typical IoT node. And we assumed, because you need to make a number of assumptions doing so, we assumed that it would operate for 10 years and the typical energy consumption would be mixed grid. So the energy consumption that the device would consume during the operation. And here you see that the expected or global warming impact of the device, of the full node, is mostly more than half is generated by the PCB and the production of the PCB. The PCB, which includes the ICs and the electronics. So you see that this is more than half of it, has nothing to do with the operation of the device, it has to do with the production of the device. You see that the orange part in the bottom, if I can try to have a pointer, that would of course help. The orange part over here, that's the end of life. So there is some part of the global warming potential that really comes of the fact that the end of life of these devices has an impact as well. You can see that the casing has an impact. Energy consumption during operation actually is a rather small impact at this moment. And then you see that the battery, it's not dominating, but this is only the global warming potential. And what this is not giving you is other elements we should consider, like toxic materials which are in the battery, maybe also scarce materials that are in the ICs and in the electronics. Other things to consider is clean water that is used in the generation, the production of the electronics. So this is only part of the story, but I think it gives interesting insights. It shows that energy consumption in operation of the devices, IoT, is not big. And my colleague of the energy department, just one floor below me, he did a calculation. He says, with your millions of IoT devices, globally, we could provide them energy with 2 hours of one nuclear plant, and we would have the overall energy consumption of all the IoT devices covered for the whole world. So in his opinion, this in absolute terms is not that big compared to many other things that we have. And of course, he's working on the smart grid, he's working on e-mobility and so on. So he thinks everything we do is very small. So the energy consumption of the IoT devices in operation themselves is not what we should consider a big ecological impact. But we should be aware of the other things. We should be aware of the toxic materials in the batteries that could just remain everywhere where we put them. We should be aware that the electronics production is not negligible and the end of life. So what can we learn from this preliminary assessment? Well, if we want to reduce the overall ecological impact, one thing is make them live much longer. If we make them live longer, maybe the part of the energy will become a bit bigger, but the other things will go down gradually. If we can make them live longer, and if we can make sure that we do something with them at end of life, then we would actually gain a lot. So the insights, and there are more than the ones we put here, is that the energy consumption is not that big. But the PCBs and the ICs might have a really considerable impact. And we have to be aware that the production of electronics, definitely for these kind of devices, is rather dominant compared to the other parts. And then the battery, it is toxic, it's finite, and although the battery itself, you could say, is not dominant, it's often the reason that we throw away the rest, or that we forget about the rest, that we forget about the end of life, because the battery is done, and we maybe don't know anymore that there is a device somewhere and where it is. So what is the problem with conventional IoT? Well, we have made it to be convenient. It's this vision of the smart dust. You just spread it around. You don't have to worry about it anymore. There is this fire and forget idea that you just put it somewhere and you can further forget. Well, it's not what we want today, because we now know that there is waste if we forget about it, and that we should make them live as long as possible. If possible, repair to reduce the impact in absolute terms of the electronics, and that we should avoid that there are valuable and harmful components that are left in nature. So this was, I think, something we like to say maybe even 5 years ago, but we know by now that this is not the way forward for these devices. So what we should do in the end, I think, is move towards a circular IoT, and energy neutral devices can be a very interesting part of that. First of all is reuse. Let's make sure that we design, that we have concepts such that the device can be reused. Some parts are very generic. Let's make sure they have a long life, that if they are broken, we can repair them. But most of all, the typical first thing that will happen is that they run out of energy. So let them work much longer, let them have a much longer life. And energy neutral devices, the way we have defined them, could have theoretically, of course things will break down, an indefinite lifetime. And that's going to help a lot in the overall ecological impact of the devices. And then I think in the third phase, the first phase, the reuse, I think is in the design phase. The second thing, the longevity, is in the operation phase. And in the third phase, in the recovery, let's not forget that we put some electronics there, and let's avoid that they are wasted. So we should guarantee the recuperation. We should have some way to automate that, to know where devices are and when they are out of operation. And one of the things you could do is consider that a drone may pick up the devices, or at least the parts that are harmful for nature or that you want to recycle. So that's a broad view. Now, the energy neutral devices, what could we do to extend the autonomy of these devices or make them indefinite lifetime? It's harvesting energy out of the environment. And if you look at what is possible to get things from mechanical sources, thermal sources, radiant sources, we have a graph here, and you see, of course, as we know, this is not the y-axis, is not a linear scale. The solar energy is the most interesting one, is the most efficient one. If it's there, of course, if it's not dark, if you're not inside and so on, solar energy is the most productive. Even inside, radiation energy can be interesting. You see that many of the other things that have been named, there's not a lot that we can get from it. These are really low power densities, and either you don't need a lot of power. Vibrations, for example, on a car and a tire pressure sensor, that could work. But if you have very little vibrations, it will not work. People have tried to make things work based on movement of people and so on, and thermal things as well. It's very difficult. So many of these harvesting sources deliver very little, and the ones that do are mostly radiation-based, like the sun. Not always useful or usable if it's dark, or if things are in environments where there is no sun or no light. And another thing we have to be aware of is if you introduce, for example, a small solar panel, it will need extra devices, it will need electronics, not only the solar panels, but you need rectifiers, converters, and so on. So it will have by itself extra electronics, extra hardware, that will also increase the footprint of devices at first to some extent. So it doesn't come for free. So then what are other ways to work with? Well, let's see how we can get energy neutral devices working for a longer time. And one of the things we consider is to have a kind of flying doctor approach for sustainable IoT, is that we fly in the energy. We fly in the energy, and we see that there are several ways to do that. We have worked on wireless power transfer with RF waves. Many of us have, and it's still a struggle, I think, to get sufficient energy there, but there are some new vistas. And another idea we are investigating is that a drone could fly to recharge devices on the spot. And I'll give you some results on both of these approaches, both with the intention that there could be energy neutral devices that would stay in spot much longer. So the three approaches we are considering, the first one, and it's not a coincidence that this one is closest to the source, I would say, is to transmit RF to the devices. And we have here drawn an array because we'll see that if you don't have any beam forming or beam spotting operation, it's very difficult to get any sufficient energy over a wireless power transfer with RF waves. The alternative is that you fly a drone, and the drone could also do wireless charging, but from a much closer distance. It could be magnetic coupling resonance, which has a much, much higher efficiency compared to radiant far field RF transfer. And the last option that we also are considering is that you would replace batteries. So instead of recharging the battery on the spot, which it is energy consuming for the drone, it has to hover, it has to wait there. If you could just replace batteries, you could also use other batteries with higher density. That's another option. So you could say maybe it's no longer really an energy neutral device because you are replacing a battery. It's a border case, I think, but still serves the same thing, that your device would have a much longer lifetime and would not be wasting so much electronics and everything that comes with it. So I'm going to be very short on the results. If you have questions, you can contact me. If you have a single antenna system, uncoupled wireless power transfer radio, but with a single antenna, taking into account the path loss, taking into account the limits of the standards and the ETSI standards, we see that what you can achieve in terms of distance is very low. For example, the green curve would mean that we get 0.1 milliwatt at the receiver. At the transmitter, we have 6.5 watts. So you see this is very inefficient, clearly. The maximum we can transmit is this 65 watt. This is this red horizontal line. And you see that in order to get something of 0.1 milliwatt over the air, we can only get 4 and something meters. So there's not a lot of distance we can do if we take into account all the actual constraints we have to be aware of. A real harvester and the limitations of the standards and the regulations. So what we then did in the Reindeer project is work with large arrays so that we can not only beam form, but we can beam spot. So here you see a simulation results in a 3-dimensional room. And the result you can see is that if the energy neutral device is on this point, that we can really create a big, clear spot in energy and have a better coverage, a higher transfer compared and a higher efficiency compared to a single antenna system. Show you a short movie. This is the real experiments that have been conducted, where you will see that, well, we will move the device. We see that there is a device that can be either based a beam spot. You see that the beam spot is really measured. So we have been measuring on several places. The red spot, it goes very fast. The red spot is where the device is. And then you see that the power measurements actually show indeed that we are creating this spot. I'll show you the measurements here. So in the line of sight, you see the red dot here is where the device is. There could be most of the power received here. If we do geometry-based beamforming and we take into account multipath components, we can really beam spot in a better way. So we also use the reflections for beam spotting. Here we only use the directivity. And in the third one, we use several, many more multipath components. You can see that we can create even a better spot. The ultimate thing would be that we can reciprocity-based beamforming. A lot of theoretical results do that, but then you have to have the channel state information. And then you can see indeed that we can come up with a very good spot that has in several meters, much more power than we could do in another single antenna system. So I think these are nice results, but we stay in the meters rather than the 100s and kilometers. So if you want to go further, we need another approach, and there we looked at a drone flying in and doing wireless power transfer from a much closer distance. All our calculation took into account the energy that the drone needs, the distance has to go, has to come back, it has to hover here, has to wait. We took all that into account. We did not yet optimize for a drone that could visit several IoT devices in the neighborhood, so we really calculated the full distance. We took into account the weights that we need for battery swapping and so on. So if you want to know the details, we try to be quite complete. And we try to calculate the efficiency of charging and swapping, comparing what you deliver versus the total thing you consume. And you see that here, considering up to kilometers, flying the drone there and charging on the spot, we can do things that are, compared to RF-based, much more efficient, even taking into account the consumption of the drone. And clearly, we can get much, much further in distance than what you would do with RF-based power. And if we would swap...
wrap up.
Yeah, I will wrap up. I'm almost there. With swapping, you could do even better, but this is being further investigated. So I'm coming to the wrap-up. What are the lessons learned and lessons to learn? I think overall, we can say, if you look at the initial LCAs and so on, compared to what you could save in energy and mobility, it definitely makes sense to invest IoT devices. They have an impact, but they can have a much bigger positive impact than what there is their own footprint. And we could get to Systopia, I think, for many applications if we have IoT invested. Regarding energy neutral devices, there are ways, I think, to make sure their life is longer. It's still important to not forget to pick them afterwards. Possibly best to avoid that you need a car for that. You could use a bike, or you could fly a drone. In future work, we need to integrate the energy neutral devices in the wireless networks, also in the intelligence and the operation. I think this is the vision of Ambient 6G, and I hope we can let you know more about that. And also, I think for the sustainability impact, there's work to do. We do LCA, but there's missing things. We need to do more than just the global warming. We need to know about the materials, the toxic materials, the water consumption, and so on. So there's work to be done on that. I think we need to better understand how we can help applications and the verticals. And I think also, last but not least, I think Europe really has a strong position in understanding. And I hope that we can exploit our strengths and the strategic orientation we have in Europe to bring it into a competitive advantage for Europe as well to have this approach. These are things we are handling in the Sustain 6G project. In conclusion, I think it's a good time now to make sure we choose a good direction for IoT, and you can make sure that we deploy them, that it is not something like smart dust becomes smart or toxic waste, but that it can really be a smart application. Shall I stop sharing, or should I consider there might be questions?
So if there are questions, please post them in the chat. You can answer them there. I think we need to move on with the agenda. But thank you very much for the presentation. It's very interesting. For the next presentation, it's from Hexa-X-II on Foundations on 6G Smart Network Management Orchestration Enablers by Ricard Vilalta.
Thank you, Patrick. You should be seeing my slides correctly.
Yes.
Thank you. So thanks for the introduction. The topic for today is, as Patrick has said, it's about the foundations on a 6G smart network management and orchestration enablers. So this is maybe related to the previous talk where we said we need more intelligence and orchestration for sustainability. We have at Hexa-X-II, we have been taking a look at how should an MNO, a management and orchestration framework, look like. And I want to do some shameless promotion of our latest results that we will be presenting this month, at the end of this month. The D6.5 is the final deliverable in our work package dedicated to smart network and management systems towards this the final results. I will be presenting results from this deliverable, which will be available at the end of the month. And as you can see, I have placed here a picture of what we call the 6C Smart Network Management Framework. This has been the main contribution of this Work Package 6. Then we will be presenting how different of the framework components have been implemented and evaluated. And also I will be discussing on some implementations based on this framework, where we can see different enablers and elements of the framework combined together, how we have combined them, how we have tested them. So this will be the outline of my presentation, and I hope that you enjoy it. So first, as I said, we focus on describing the smart management framework as a whole, and I will provide a general description of its structure and walk through the different components. So we will follow this approach where we go from top down. I will start and I will try to describe this figure with a lot of details during the first part of this presentation. You can see the framework below, and we have main technical enablers that have been grouped in different categories. This framework is designed as a supporting structure on which the management and orchestration systems for 6G can be built, offering them a system of rules, ideas, and innovations that can be used to plan and decide on such systems. So autonomicity is a key focus of this framework. If we take a closer look in this framework, and we start with the overall MNO solutions, we see that first we discuss on MNO related functionalities. In here we have the relationship of the different functionalities that are commonly found in management and orchestration systems. I will not go into details on them because they are quite well known, and they range from service, resource provisioning, assurance, monitoring, and so on, and are represented by the color numbers in the list in this figure. You can see that we have mapped each of the different enablers in our framework towards one of these related functionalities. Of course, network assurance, for example, is provided by the combination of different enablers in this framework. So you can see some of the enablers with several repeated functionalities. Then, if we take another look, we can see that beyond these common management functions, the framework also includes cutting-edge technologies, such as the extensive usage of AI/ML, zero-touch automation, through closed control loops or digital twin creation mechanisms, among others. So this is what you will find in here, for example. Then we have the technical enablers grouped into two overall scopes. One, those targeting the whole network continuum scope, and the others considering the scope of specific stakeholders, which are in this inner rectangle. So we have in the overall functionalities, we cover the overall cloud continuum, and then we have here the specific stakeholder scope. Enablers have been also grouped into four main categories, which are highlighted in red. We have the overall MNO solutions. We have that include enablers integrating an extensive set of MNO mechanisms. We have the overall functionalities. We have the specific systems, and then we have the algorithms. So you can see the overall functionalities, the overall MNO solutions below, And then in the center, on the left side, we have the specific systems, and on the right side, we have the algorithms. So this is the first instructions to understand this framework. Then, if we take a deeper look into the overall MNO solutions, we can see that these enablers integrate a rich set of MNO mechanisms that target to manage and orchestrate network services and resources across the whole network continuum. This overall term here refers to the extensive set of functionalities integrated in these solutions. Two approaches are offered in this framework, namely hierarchical and decentralized. The hierarchical approach is based on a multi-agent system for multi-cluster orchestration and includes a centralized end-to-end orchestrator and distributed agents. Instead of this, the decentralized approach targets to manage a network and services in a fully automated way. The main challenges addressed by these two solutions are the envisaged highly distributed and multi-stakeholder ecosystem towards 6G, and the integration of the extreme edge domain, which has some volatile resources, cloud-native scale, and a varied kind of devices. So the key concept here is to utilize the combined computing and storage capacity of the extreme edge domain to distribute workloads efficiently, to reduce data communication needs, lower latency, potentially surpassing the current 5G capabilities, and to enable new business models for the stakeholders. When we take a look at the overall functionalities, this section outlines 5 key functionalities in the framework that they are described and complement and between each of them and propose this overall solution, and are also in the scope of the entire network continuum. These are the following. So we have first monitoring and telemetry. This is very important as it enables the integration of diverse monitoring protocols and user-defined metrics across various network domains, and supports AI/ML models and feeds heterogeneous multi-domain data for improved decision-making and proactive network management. When we say proactive network management, we can reach, without monitoring and telemetry, we cannot reach autonomicity. So we need this, and this is an important significant component for this for the MNO framework. Then, of course, we need to do something with this data and process the process data. So we have the real-time zero-touch control loops automation and coordination mechanisms. So we are intended to automate network management through adaptable and configurable control loops, integrating AI/ML actions, and allowing these autonomous responses to real-time network changes and proactive optimization actions. So this is not only about real-time zero-touch control loops, but also the coordination of these control loops and how they because they are times they can clash, they can have different decisions. So coordination is also needed at several layers in for the control loops. Then we have the management capabilities exposure that facilitates cross-domain connectivity. We also have the SLA-driven federated orchestration, and we have the trust management mechanisms, which allow us to integrate trust evaluation in the MNO framework. If we take a look at the MNO framework specific systems, this block groups the key systems that operate at a stakeholder level in the management framework. So the following enablers that are included here are the third-party resource control separation system, which makes possible to establish separate MNO spaces per tenant in a multi-tenant environment, for example. Also, the user-centric service provisioning system. We also have a network digital twins creation mechanism that creates the virtual models of network environments for safe pre-production testing, for example. We also have the sustainable MLOps asset, which helps us to create automated AI/ML-based service workflows, which enables also the monitoring of the energy consumption and different stages of those workflows. We have the network programmability enabler, which helps us with the integration of software-defined network technology in future 6G networks with a cloud-native model and offering new interfaces for emerging devices. We also have a specific system, the secure AI ML-based control, which supports intent-based management systems, which are addressed in the context of Work Package 2, for example, to enhance their security. Finally, last but not least, is the privacy-preserving data analytics enabler, which ensures that sensitive data protection during the different AI/ML processes and enables privacy-preserving analytics. This section of the framework regarding algorithms includes this set of algorithms for future 6G systems and emphasizes the importance of incorporating certain algorithms into the management framework with the primary focus on AI/ML algorithms. So the different selected algorithms that we present are the following: the ML-based configuration recommender, algorithms for efficient network and service function allocation, multi-domain federated learning algorithms, multi-agent with reinforcement learning algorithms, and also explainability algorithms for error control, which is quite significant because it provides human understandable explanations for decisions that have been made by reinforced learning-based control algorithms, which is very important because it enhances transparency and trust on the automated decisions. So we have not only think on the framework, but also on the related KPIs that can be obtained and can be measured in this framework. So this is the figure that shows the mapping between the impacted KPIs identified in the previous deliverable and the different assets of the management framework. So in the middle, you can observe the list of KPIs such as scalability, latency, flexibility, service creation time, reliability, and so on. I will not go through the whole list, but I want you to see that each of these KPIs can be measured in some sense with some of the different assets of this framework. So for example, if we take a look at monitoring and telemetry, we can see that specific KPIs are scalability, reliability, and latency, automation, and flexibility, for sure. So, and this can be applied to each of the different enablers. The values of these KPIs can be found in the document in that will be presented by end of the month. And they will be also included, and some of them measured in the POCs that we will be presenting at the end of the project in the context of Work Package 2. So let now me jump to the framework components, implementation and evaluation. This section describes the implementation of some of the enablers that are part of the management framework or certain specific features in these enablers. Some of the early implementations were reported in the D6.3, which is available, and we have provided more information on those implementations in the D6.5 that will appear by end of this month. So we recommend that you take a look, as we have been focusing on these framework components. So AI-enabled real-time zero-touch control loop analysis function, for example. We have some specific implementation for this. We have the penalty-based management of concurrent service CLS. We have the conflict detection for the reactive activities requested by the closed loops, which this relates to what I was previously explaining of control loop coordination. We have the human-assisted training of cognitive closed loops functions for network automation, which this improve our trustworthiness on the control loop automation, putting a man in the middle. We have the sustainable MOps. We also present some results on Edge Teraflow SDN as a network programmability framework. And finally, we present also some results on monitoring and telemetry, also including energy measurements, for example. So the last section I wanted to talk about today is about the implementation based on the framework and evaluation results. So this section describes how some example implementations based on the framework I have been presenting today are showcasing how the framework can be used in practice. So they are 7 different implementations that have been performed, which combine enablers of the management framework. We can see we have put them all here. Of course, if you want more details, I recommend that you take a look at the deliverable that we will be releasing, because to go one by one, it was impossible today. I wanted just to mention the different topics, but you can see that each of them is an instantiation of the framework using several components. And they are very interesting, and I recommend that you take your time to read about the different implementations that are more suitable to your interests, such as the first one is the usage of the management capabilities exposure system. So it showcases the usage of management capabilities exposure enabler, considering different use cases, such as the integration of a vertical industry and failure detection and recovery scenarios. We have also a second implementation focused on orchestration on the network continuum. This showcases different MNO scenarios of the network continuum, including the proactive migration of service components, MLOps, service federation, and trust management. Another of the interesting implementations is the functionality allocation in a cobot-powered warehouse inventory system. This focuses on orchestration of a network service providing an automated inventory management solution for the accurate and efficient warehousing operations using collaborative robots. The fourth implementation presents an ML-based configuration recommendation for energy saving. This provides a fully automation closed-loop-based solution for correcting flow misconfigurations in a scalable way in deterministic networks. The system takes autonomous decisions for cells sleep and wake up. The fifth implementation focuses on resource assignment for federated layering, showcasing how telco operators can leverage and reach data sources of connected devices, and on the deployment of edge compute resources to provision AI model training as a service, such as in line with the compute as a service paradigm. The sixth one is about flow reconfiguration based on dynamic monitoring and closed loops in deterministic networks. And finally, the seventh one focuses on edge conversions over federated resources for the computing continuum and explores the capabilities of the Camara Edge Cloud APIs in the management of the compute resources in the network continuum, and the possibility to extend them to be used with federated resources of external administrative domains. So I hope that you have enjoyed this implementation, and now I wanted to conclude with we have had the objective to contribute to the design of the Hexa-X-II end-to-end 6G system blueprint. And for that objective, we have developed this smart network management framework. We have had define all the different framework components, the different solutions, general functionalities, and also included some specific systems and algorithms. We have provided design and evaluation with, you will see in the deliverable, detailed component design, evaluation and KPIs, different workflow scenarios, and also KPIs to be measured. We have provided different key innovations. Some of them are listed here. And also we have included a smart network management framework, introducing novel approaches. If we think on recommendations for the future, and this and the following slides provide an overview of the next steps that should be considered for the development of the concepts after Hexa-X-II finalization, so that they can be handled in future iterations. As our work package is ending by end of this month, we think that providing insights and recommendations for the future was necessary. So there are some trends and future work that for the overall MNO solution that need to be considered. We have considered that the multi-agent MNO techniques, for example, that also to some of the decentralized MLO techniques to be extended, that these are both important. Also, the monitoring and telemetry framework is of significance. Also, we have planned refinement of the support AI mechanisms for automation and the promotion of implementations towards standardization. It's very important. We are having this week in ETSI, the AI conference, to work towards a standardization of the different AI ops and ML ops models. It's important for the benefit of the community. Also, regarding zero-touch network automation, we could include new descriptors that could be used for unified closed-loop modeling. That's something that is on the way, and also new mechanisms to support real-time closed-loop functions and governance, which need to be combined with the monitoring and telemetry functionalities. Regarding the management exposure capabilities, we have been presenting the integration fabric, which was inspired by ETSI's ZSM model. Also, some of the future trends that we also recommend more details are the network digital twins concept that have been introduced in Hexa-X-II, and the sustainable MLOps approach that we have been discussing, some of the network probability solutions, and the third-party resource control separation and user-centric service provisioning mechanisms that we have explored in Hexa-X-II. So just to finalize, more information about the activities that we have been doing regarding smart network management and orchestration enablers, they can be found in this set of different deliverables, which I have been commenting during this presentation. So I will be ready to answer any of your questions in the chat. So thank you for your attention.
Thank you very much, Ricard. And in the interest of time, so let's take any questions in the chat. We can move on to the next presentation. It's on 6G Cloud by Chen Tao from BTT.
Patrick, can you see my screen?
Yeah, and I can hear you.
Okay. Thanks to invite me to present 6G Cloud, this system-oriented architecture. This work is from 6G Cloud project. My name is Tao Chen. I'm the project coordinator. Also, I'm principal scientist in E. So today I'm talking about. Okay, let's see. Turn the page. Okay. So first, let's talk about what is 6G Cloud about. So 6G Cloud, we do a research on two important things regarding 6G architecture. One is to design and also to validate this AI native and cloud-friendly 6G architecture. We more focus on the run and the core together, also taking into account management and also orchestration system, also AML framework. The second part is that this system, since we said with our service-oriented architecture, so will be on top of cloud environment. So that means it's a multi-stakeholder, multi-site cloud environment. So we try to also manage that to provide a service to the 6G network on top. So this is a SNS JU phase 2 project focused on this system architecture. So we have 12 partners from 8 countries. So from the right side, you can see the list of our partners. So this project we started about 1 year ago. So it's about a 30 months project. So for 6G Cloud, so let's begin with the cloud. First, let's take a look about this cloud landscape. That's why we built the architecture about on top of a cloud system. So if you see that currently that this IT industry, that is the cloud is become so popular, right? So we have a central cloud. Also, we have a edge cloud, and also for base station side, also when the cloud is this edge is also work along with the base stations. But even go beyond that, we have also this use equipment side that we are now to have this kind of virtualization technology on top. For instance, in the car, that we also can run very powerful applications, so virtualize the environment on top. So that means that can be extended to also the cloud to edge. So we can manage all the cloud. So the question is that could we also move the 6G network on top of cloud. So if not all part of the 6G network, how we can utilize the cloud environment to really get benefit for cloud. For that, we see the evolution of different generations. So start from 4G, that we see this NFV is already introduced in 4G period. At that time, that this watch machine is introduced. That means the whole operator system is running in the one watch machine, and then application can run on top of that. So from that time, this in the 4G, so it is very limited to utilize this virtualized the network technology to run the system on top. But when we move to 5G, that we have this run disaggregation, that's split run into the DU and CU, and for the CU, and some part of DU can already run in the cloud environment. So also we see the movement that instead of virtual machine, also they have contain as common this cloud-based application or cloud-based network function more effectively. So for 6G, we expect that they will move one step further. So there's more cloud-native network functions run on cloud, and especially for the run part, that because run is only partially that run the cloud, and then we expect that run could take a new approach, can connect with this service-based core network, so it become more cloud-native, and then for this new generations, and this automation could happen in the cloud environment, and have this cloud-native automation to really flexibly deploy the network. So this is the evolution of the mobile network. So so why we need to do this kind of evolution to move to cloud? So we also see the limitation of this 5G architecture. So so you see that for the cloud network that we already use the service-based architecture, that is cloud-native architecture, right? But on the run side, that the traditional approach, they use this reference point architecture. That means the different components, they have an interface between each other, and they use point-to-point link to each components. So this is not a cloud-friendly design, because when you move to the virtualized environment, you have this cloud resource, and then if you still keep this point-to-point interface, that you basically you cannot really take advantage of this flexibility that's provided by this cloud environment. So let's expect that this architecture should be also changed in a way that to really utilize the new infrastructure that to really share the network's resource. So to support that evolution, that in 6G Cloud project, we deal with these four key concepts, key aspects. The first one is that how we can really leverage the power of cloud infrastructure, because there's a different cloud, as we showed before. There's a far edge, and also there's a regional edge, and also there's a central cloud. So this edge, this cloud come from a different stakeholder, and also it come from located in different site. So how we can really manage this different cloud? We need a cloud continuum framework. So that means we can manage the cloud in a uniform way, and then can provide this resource really to the network functions. Then next aspect is that we need to move this cloud native design really to the radio network. So of course, there's a lot of debate that how radio network can really be fully cloud native, because some functions like this radio unit cannot be put into the cloud environment. But still, that most of part could be cloud native. That is not just like now we just to virtualize the current DUC in the cloud, and that is not cloud native, right? So if we can move that part to radio network, and we can make an end-to-end the 6G service-based architecture, then we can have flexibilities to really utilize the cloud, and this how to move the resource in different network, different part of the cloud infrastructure, and make very flexible network deployment. But if we put this cloud infrastructure and also this 6G network for run and the call side together. So there's a very serious this resource management problem. So we really need a management and resource orchestration framework that to manage not only the cloud resource but also the network resource. So that's one research we need to do and to see what is the problems there and how to define this framework. And also for this complexity that also for network automation as a key feature that to manage a complicated network, right? So we need the intelligence to manage the complexity. But for the intelligent part, so it's how to manage also intelligence is also important questions. So we need this AI ML framework to do this lifecycle management for AI and also the AI workflow. Then for the motivation to move this service-based design to the run is, so first, what is service-based architecture that for run? So that means so network functions, we disaggregate the network functions to basic unit, and then we can make every functions as a service. Then from there we can combine that through this unified API that form the network entity or network node. So and also the information that within these network functions can exchange from some message bus, or let's have a uniform interface to exchange that information. So this can provide at least scalability, because if you want the new functions or new capacity, you can add a new network function in the cloud infrastructure and use the same service bus. And there's also it's very natural that to implement on cloud infrastructure, right? Because this design is really a cloud native design. And also it's easy the deployment and also allow to do this CI/CD to extend also network features and in a continuous way. So if you see the service-based architecture and also the reference point architecture, there are two major differences. One is this. So the procedure that inside the network function is different in that service-based architecture. They use uniform the procedure that for the same function, the different network functions. But this point-to-point architecture, so they duplicate the procedure for each network function. So it's not effectively we use the design. And also for the interface that service-based architecture network functions can use a single set of API for all and to access the function inside this network functions. But for this point-to-point architecture, so that each new component they need a new interface to define. That's not flexible, especially if you want to extend the network and you have to define a new set of interface. That is not effective. So you can see that here is just an example of how service-based design for the core network. So you see that there has a service bus on top, in the middle. So these data functions that use the same API interface to connect to this service bus. So there are different group of data functions. That's data for service management. Also this signaling and also admission and also session management. So that means that this kind of network functions in fine granularities can develop it and also plug into this service bus, so extend the network capacity, right? Also the functionalities. But if you see that for the run part, the run is just a box here. So how the run also can have a similar design, then we can combine different network functions and to form this customized, the network service that's for in the use. That is the flexibility that could be provided if you use this native cloud native design. So so for the challenge to bring this service-based design to the run, so there are these 5 challenges, but there are more. Of course, that's because for the core network and the run has more requirement on the real-time process and also the low latency requirement. So this constraint, that's how this service-based design can really implement to the run, because some very data intensive process may not good that to just put into this kind of microservice. Right? And also there's limited resource in base station and also the run node that if it's in the edge. So if you put this design, then you have to see where to find the computation power to really do all the process. That's challenging. And then also that's the run part is very diverse environment. It has this different RU part and also the distributed this DU and the topology is very complicated. So how to really orchestrate different resources is a very serious challenge there. And also if you use service-based design, signaling is the issue because there's the service bus and how service bus and message can really transfer that in single service bus. Is there any bottleneck there? There's also the question need to be investigated. And then also have security and trust issues to investigate. So put all these challenges together. So in 6G Cloud, we have proposed several options for service-based architecture that for the ROM part, and also we investigate how to integrate that with the core network. So for this design that we see, so first we put this service-based design on the control plane. So for the use plane, we follow the same approach as before, because the use plane has more data intensive this process there. So it's a challenge that to also use this kind of service bus approach to transfer data. But for the control plane, you see that on top we just to say that some control plane functions are put into this cloud native functions, so they can link with this unit that on the bottom and that can, what to say, to at least they can support that unit that in DU, CU in the traditional approach, and to form a complete this protocol stack to be functional. But on top of that, some new network functions, we call this 6GC, the functions can be extended, also can be combined with the original network function to extend the capability of that. And also on top of this service bus, we have these new functions like AI functions, and also this apps functions is we call this app functions is actually kind of control functions that can control the network functions behaviors, and also can extend some new control capabilities for the control plane. And also we have this exploration network functions also linked to this service bus to explore the network status, and that's to the outside, to third party, and then try and extend this capability of the whole system. So in this case, as you see in this architecture, also we see that UE could be also part of this service-based architecture. But of course, that is also a place that we need more investigation. But we think that if UE has capability, that can also host this virtualized this network functions, and then we can also link that together. Okay, so for the run and call that. So we propose that they can be linked together, but this can be in the same service bus. But the way we can do is also we can introduce a message gateway that we isolate the call and run this service bus. So the message gateway can transfer and isolate and this two domains. So this provide also this kind of separate of concern that in the network design. Okay, so if you see that this service composition, so that we can disaggregate the network functions to basic network functions, for instance, synchronization service or schedule control service. These basic functions can combine, right? And they can combine to composite network functions. And then for this composite network functions, they can use to support the network slice or different slice, maybe the different combination of the network functions. And this network slice this formed by a service chain that with different functions can also link to integrate with the this RU, and they have some physical network functions layers to form the network service. So in this case, we can provide a really flexible way to combine network functions and provide the different service from the run side. And also you see, so the run and the call, there's need the integration. So with this service-based approach, and we also can more flexibly combine the run and call functions to form a specific network service, like the run service. So for instance, in this gateway, and so we can put some network call network functions, the UPF or other functions together with some part of run functions to then we forward a network that can support this low latency service for factory, or in other case we can move this even the run functions to the central cloud, and then we can keep the run functions and call functions all more closely and for other purpose of the network. So this integrations and so provide also one solution at how this run and call can be converged. And also we have proposed this AMF here, but it's just a box here, and that framework is provided also AM support for the network. This framework also they have their own building block, and is different from what you see in this service bus for the run. So this in this case we provide a flexible connection, these integrations, and we offer two options that for this run and call convergence. And the one options is that we introduce a service bus, a service-based integration layer between the run and the call, but the run itself use the traditional design, this point-to-point architectural design. Right? So, but this integration layers just provide some network service exposure to the call network, so that call network can get some information from the run to do some process. In this case, is just to provide the back compatibilities that to the legacy system. And the other approach is that we show in the previous slides. So we both run and call use service-based design. So in the two cases, one case is that this network function in the run can directly link to the call network service bus, so they can talk to each other and to integration. And the second case is that we use also this integration layer is provide another layer of this abstraction and also the separation of these two network element. And for the we also talk about this management, that orchestration. So it's very important to also take into account that part. So this is also one of the key working area in 6G cloud, because we have the cloud resource, and also we talk about the cloud continue. So that's how we manage this cloud resource, and also how to manage the whole network is the big questions. So then in that case that we have this work, but I'm not going to go to detail for much detail for this management and service orchestration part. Just to mention that for the management and orchestration framework, we have this MORPH. So this is MORPH to provide the service orchestration, and also we provide the management to different network instance. We call it network service, because one network service has all the run and the call, and they run independently, just like a network for one operator. And for there can be multiple network service that in the same cloud infrastructure that this need to be managed by the same this MORPH, and also this cloud continue framework called the CCF. The CCF is on the bottom to provide the cloud service management and orchestration. So that's these two MORPH and CCF have to work together to provide the management of the cloud resource and also the network resource. And also we have this AMF framework that to provide the AMF functions for the management of the service, and also for the run and the call, and for you see that in the middle that also the AI functions actually connected to this AMF framework to get this AI model distribution, or also this service from the AMF framework. So put all together, we form a 6G cloud architecture, the complete picture. So the more details, of course, we have already worked on some deliverables and some detail. If you have interest, you can go and see. And just
Chen, could you start
yes.
wrapping up? So
Yes, quickly. So it's managing the building block, and also you see the examples of design, right, based on the FCAPS, this principle, right? So each network service or each network this segment, we have one of this managing building block to manage it. And for the cloud resource management and so in the CCF, that we also have this management design. So the key idea is that we have this resource partition for cloud resource, and each partition that we have this resource orchestration to manage the resource for particular network service that's run and call network for this network service. So in this way, we provide this isolation. That's also a more flexible way to manage the network. Then let's compile with the Hexa-X-II system blueprint that they're similar. Similar layout that for these two systems that we have. And in Security Cloud we have network service, and in Hexa-X-II we have this network function layers. Then for the management and continue framework, also there's also building block there. So basically we follow some design principles also from Hexa-X design. Okay, so that's the idea, just to provide these basic introductions for Security Cloud and what is the main topics we covered in the project. To summarize that, so Security Cloud, that we talked about this end-to-end service-based architecture for 60 mobile networks. So with 4 key designs that in architecture, and then now we have these 3 prototypes to test the different aspect of the architecture, and we expect in the this later of this year we should have some results for the prototype and also for detailed design of our architecture. So if you have interest in, and you can also visit our website to get more information. So that's all. Thanks for listening.
thank you very much. If you have any question, please place them in the chat. According to agenda, we should have a break until 15:15, but let's have a very brief break now, a 5-minute break. So be back at 20 minutes past. So everyone get some leg stretchers. Let's try sharing of the next speaker during the break.
Do you see my presentation or my other slides?
It's the correct screen. It looks good.
Is it correct?
Yes.
Good.
All right, and the audio works.
Can I take a quick
Thanks.
detour on the cooking power bar? Mhm.
Oh, okay. We are getting no sound.
Hello, Erik.
Hello. Hi.
Hey, good to see you.
Yeah. Can you see me?
Yeah, I can see you. Yes, I can see
Great.
the slide too.
How are you?
Hanging in there. Busy. Are you going to the EU CNC?
Sorry?
Are you going to EU CNC this year?
I don't think so. When is it?
Oh, okay. EU CNC is in Poland.
Okay.
Yeah.
Okay.
Anyway,
I'm going to
okay.
the communication theory workshop in Venice.
Okay. I'm
That's
waiting for
the-
your presentation, okay?
Sorry? Yeah.
Right. Talk to you later.
Welcome back. It's 20 minutes past. You all managed to grab a cup of coffee. We continue with the presentation from Erik Dahlman from Ericsson on 6G wireless connectivity. Something new or more of the same?
Okay. Thank you, Patrick. Do you hear me well and do you see my slides?
Yes, that's good.
Okay. So good day, everyone. This will definitely be a somewhat more high-level presentation than the previous one. So I'm trying to give a little bit of my kind of view on 6G. Probably partly biased by my history, where I actually, of course, I've been mainly involved in the wireless part of the earlier generations. So, oops, there, no, there. So, kind of first questions: what do we need from the wireless access in the future? And maybe first the questions: what do we not need? We definitely do not need higher peak data rates. We don't need these kind of ridiculous numbers that are often mentioned, like terabits per second, etc. And I think most people seem to agree to that today. Still, if you look at what happens in ITU, etc., they are still kind of defining peak data rates requirement for 6G. I personally don't think we need even kind of lower minimum latency in terms of kind of extreme, these kind of almost ridiculously short latencies. I think it's much more important that we can get some kind of low latency, but really predictable latency, that we can really guarantee that we get like 1 millisecond instead of saying, oh, sometimes you can even get 0.1 milliseconds. What do we need? I do believe we still need higher data rates, especially for the uplink. So often I hear people saying, I mean, we have sufficient data rates. We need a lot of other things. We need kind of sustainability, blah, blah, blah. We definitely need higher uplink data rates in many cases. Simply speaking, we are quite often, we have sufficient bandwidth, but we don't have sufficient power available. And that's a quite tough problem to solve, because I mean, power is still a limitation. I believe we also need more capacity in our networks. I mean, the traffic continues to increase. We can probably not do some fantastic things by changing kind of technical details. Sometimes I feel that we need to go to more dense networks to get the capacity we need in the future. But then we need these kind of little bit new things. I mean, there's a much more focus nowadays on reliability, availability, resilience, as we go to kind of more and more. Also starts to see that our systems will be used for more kind of mission critical connectivity. And of course, we need improved energy performance. That is something that we didn't care about up till around 4G, becoming more and more important for several reasons. I would say the two concrete reasons are: one, it can allow us to deploy base stations where there is no connection to the electrical grid, so we can rely, for example, on solar power. But also, perhaps even more, I mean, the cost of energy is a big part of the overall cost of many operators. And that is then just kind of one aspect of, in general, we need to continue to chase cost for the operators. We need to be able to deliver more with less cost. I think these are important things. And there are other things as well, but at least from our point of view, these are a number of rather fundamental things that we need to continue to pursue when we go into 6G. And then I just have a little bit of an interesting question here. Of course, quite often, I mean, we talk to operators and they say, well, why do we need a new generation? And and then immediately raise this question: what do we mean that to say we have a new generation? What does a new generation imply? Of course, many people would like to assume that the new generation is kind of a big leap in technology and a big leap in the capabilities we can provide. That is typically not the case. There is a leap, of course, a leap in technology, there's a leap of capabilities, but quite often we also have quite big leaps in technology within a generation. I would even say that in some sense, the biggest technology step I have experienced in my career was when we went from the first release of 3G until this kind of HSPA evolution, where we introduced all these things of link adaptation, shared channel operation, etc. That was within one generation, but in many ways kind of bigger. I would say it was actually in some sense a significant bigger leap, at least in terms of the radio access technology, compared to when we went from 4G to 5G. Is new generation always associated with new spectrum? Typically, yes, but we should be aware of that we're getting less and less new spectrum available, and every new generation is also applicable to current spectrum. Many people say, the key thing with the new generation is that we don't need to be backwards compatible to the previous generation. Honestly, I don't think that is true anymore. I would say that in some respects, 5G is backwards compatible to 4G, in the sense that we can have a 4G device accessing a carrier frequency where we actually also supporting 5G services today. I'll come back to that a little bit later, because we will have the same thing for 6G. One thing that really is about is, of course, a new set of 3GPP specifications. If we talk about 3GPP technologies, that may sound somewhat kind of a formality and not so technically relevant, but it actually is rather important, because I would say that a main benefit of the new, when we have what we call a new generation, is really that we get a fresh start. It is a fact that many of the things we are today discussing for 6G as new things, I mean, they actually also starts to get into 5G discussions. That's the kind of all we've been doing like that. We start to talk about new things for the next generation, and immediately they are introduced also in the previous generation. For that generation, a later release. But I would say that the key thing when we go to new generation is that these features are actually being implemented in real networks. A lot of the things we introduce in later releases of 5G or 4G, they are there in the specifications. That creates a lot of interesting discussions in 3GPP, but they are never implemented in real life. But then, as we go to the next generation, they are actually being implemented in the first release of that generation. So in practice, even if on paper, actually the first release of 6G will probably not be much more capable than the corresponding release of 5G, which is then like release 20 or so. In reality, in theory, it will not be much more capable, but in practice, the networks will be much more capable. There is also a new generation gives an easy way to actually remove features using what's the point of that? There is a lot of features that come into the standard, never practice used, but creates a lot of complexity because they be mandatory for the device, etc. We can get rid of those things when we go to new generation, reducing complexity and cost. And also, there is some kind of restart of the evolution cycle in the sense that in each generation, we have an evolution, new releases, we add more and more features, but it's obvious that we are kind of leveling out and we are running out of kind of new enhancements. When you get the new generation, we start maybe not very far from where we are in the previous generations at the same time, but we can have a much more potential to continue the evolution. So long term, I would say that 6G is critical really to ensure that we have a long-term evolution of wireless connectivity. We could say that we first release of 6G, we did not much better than what we can do with 5G evolution. But then that will be what we have. We will not get very much further. When we get to the 6G, we open up for continue to evolve 6G for quite a long time. So we can get much better capabilities and much better performance in the long run. So I think, even the left one here seems to kind of, why do we need 6G? There are very important reasons for actually having 6G as a tool to ensure a long-term evolution. That being said, I think it's quite clear because, the picture of 6G starts to become quite clear now. Standardization is not very far away. Technology-wise, 6G will, at least on the wireless side, inherit much from 5G. Which makes sense. If we have done something good in 5G that works well, why just redo it because it's fun? Much better focus on other things. So there's a lot of things that we will keep from 6G, from 5G. We will have the same waveform, or at least a compatible waveform. We will not go away from OFDM. We will keep similar coding and modulation because they work well. You can't gain very much by doing something new. Probably quite a lot of the MIMO features will be the same as we have for 5G and go on. Rather, but we should be, prepared. If there are things we have noted in 5G, it's not really optimal. We can do better things. We can change things. Then we should do it. And now here I just list a few things that we have identified in terms of certain control signaling aspects of 5G. Turn out they looked good on paper when they did them, but now as we have gained experience, we have kind of implemented them. We have run them in networks for some time. We noticed they could actually have been better. Let's focus on those things and update them. And finally, of course, there will be completely new use cases that we didn't think about when we made 5G. That we need to of course, add that functionality. One is this that comes back later, this integrated sensing, which of course is completely new things. It was not on the map in any way when we did 5G. Now it's quite clear that we will have some function for support for that. We also about this resilient communication, this kind of a magnitude of higher reliability, availability, etc., will also require new things. But I think this is a key thing. It's not so that we're not. Even when we make a new generation, we don't start with a blank sheet. We start with what we have and build on that. Of course, we did the same thing with when we did 5G. we didn't start on the blank sheet. We inherited a lot of things from 4G, and it will be the same in 6G. This slide just show a number of still kind of what we see as different technology components. I will not stay on this much. I will go through some of these later on. But I mean, as I say, I have mentioned here waveform. We don't see a change of waveform. We will inherit the 5G waveform, perhaps some extended numerology. You see here things like duplex flexibility, a lot of talk about that. It's already discussed in 5G. Distributed MIMO, of course, a lot of and there will be a lot of things that kind of relate to this artificial intelligence and machine learning, etc. Just one thing, spectrum. You've probably seen this before. We always have new spectrum when we ever go to new generation, and we are kind of always going upwards. But we are in some running out spectrum. So a key spectrum for 6G radio access will be the same spectrum as we're today using for 5G and even 4G. Especially in some sense, I would say, both these in some sense. I mean, the lower frequency spectrum below 7 gigahertz, that will remain exceptionally important in the 6G era because that's the spectrum will provide coverage. Millimeter wave, that was a big thing in the early discussions or the early standardization of 5G, but which have not turned out to be such a big success as many people hoped and claimed that it would be. Will be, hopefully, maybe we can fix some of the things as we go to 6G. That spectrum will be better utilized for 6G. But these are spectrum that are already being used for 4G and 5G systems. And that's important to have in mind, that they are already occupied in some sense. I will come back to what that implies for how we design 6G. Then, of course, there's a lot of talk about this new 6G spectrum, centimeter wave, between 7 and perhaps 24 gigahertz, typically mentioned. We see probably the lower part of it is more important because that's where we get better coverage. Sometimes seen as the golden spot or golden frequency band, golden band for 6G. Problem with that one is that it's unfortunately not very much available. It's used already today by a lot of other things in different parts of the world. Satellites, radio links, military, etc. We should still focus on this spectrum, but I think we have to be aware of it. It is occupied, which also raises problems, but also raises a lot of interesting research questions and technology questions. Finally, we have the sub-terahertz spectrum that was a lot, I would say, quite a lot of talk about during the early days of 6G. People come in. It was kind of the natural way to go. In 5G, we went to millimeter wave. In 6G, we go to sub-terahertz. There is substantially less talk about that now. I would say it's quite clear that spectrum will not be part of at least the first releases of any 6G standard in 3GPP. Maybe in a later stage, but it's simply so that it turned out challenges for millimeter wave was so if millimeter wave would have been kind of worked exceptionally smooth, then it would have been more natural to actually go up there. But today, even we have too many challenges already for the millimeter waves. So we should focus on these. But coming to then, this spectrum is already actually used. I mean, we go to the spectrum sharing, which I think is actually a very important part of 6G. First, 6G have in the same way as 5G can coexist with 4G in the same spectrum. We have to allow for 5G, 6G spectrum sharing. It must be possible to deploy a 6G network on top of a 5G network, same frequency band, same frequency. Otherwise, we will not get a smooth introduction of 6G in existing spectrum. In practice, we will not get any substantial 6G deployments in lower frequency spectrum. We will not have any 6G services with wide area coverage. And there's another reason to actually staying with the 5G waveform. It's critical to really that if we have the same waveform, they can be put on each other and we can get efficient and very efficient spectrum sharing, especially as we were in some sense quite smart when we did 5G. Because 5G we focus very much on this so-called lean design, where we have very little, how to say, always on signals. You can really put these on top of each other with very small, how to say, additional overhead. The other one is that, and so this we already done for when we went from 4G to 5G. It will be much more efficient as we go to 6G. The other one is is about coexisting with other usages, because it becomes more and more clear. I'm not sure we will ever get any kind of dedicated spectrum where we just have able to deploy 6G systems in the centimeter wave band. Probably we have to ensure that we can coexist with satellite systems. We have to ensure that we can coexist with the radio links. I'm not sure that requires extremely advanced methods, but I think it's really something where we need to work on. We need to ensure that this can be done, because this is something we need to get access to the centimeter wave spectrum. But this is one, one important area for action for 6G. Ensure that we can coexist with earlier 3GPP technologies or earlier cellular technologies, but also ensure that we can coexist with other types of systems that are operating in the same frequency band. Something we haven't really had to do before. AI for communication. I have to admit I'm not an AI expert, maybe because I'm slightly too old for that. So maybe I am kind of too non-visionary on this. Anyway, I mean, AI is clearly, I mean, it's exceptionally progressing exceptionally much during the last 10 years. To the extent, and some that people think that will solve everything. As I see it, as I understand it, what AI really comes in, machine learning comes in, is we have these kind of high dimensional problems for which there is no good model for the problem. Or if there still is a model, it's very difficult to derive or impossible to derive some kind of optimal solution. But if we solve a problem, we have a good model of the problem, and we can derive the analytically optimal or close to optimal solution for that problem. Clearly, I mean, AI cannot do better, because by definition, AI cannot do better what is optimal. But there are a lot of problems that are of these kind of categories that we have no good model. We are today relying on gut feelings to solve them typically. And on those, I think AI can provide a lot of kind of new insights. Just some examples, I mean, because they already start to work on this. I mean, beam management, such a problem. How do we do advanced beam management? That is kind of exceptionally complex problem if you try to solve it analytically. Scheduling is the same. Going even further up, I mean, on all the mobility procedures where we today rely on gut feelings, or even more if we go to network deployments where we really rely on gut feelings today, or rely on just experience. I think those are the cases where really AI can come in and help us to do things, to do the networks so that they are more efficient, or we have a reduced cost for the networks. On the other hand, I am less kind of enthusiastic or less hopeful that we will have fantastic advances in terms of physical layer processing by means of AI solutions, because there is things we have quite good models, and we can quite well derive algorithms that are quite close to what is optimal for those models. Another question, of course, is this kind of what kind of AI do we have? I think at least sometimes people talk about one-sided models versus two-sided models. One-sided model is essentially where we are running an AI algorithms at the network side, or we're running an AI algorithm or AI model at the device side, and they are kind of not directly interacting with each other. This is a relatively straightforward problem with quite limited standardization impact. The one that is much more complex is this when we have some kind of distributed model that runs both jointly at the base station, at the network and the device. How do we do interoperability in this case? I mean, it's probably decently okay if this infrastructure device comes from the same vendor. Otherwise, we need to standardize some kind of interoperability here. And that immediately then starts to impact what flexibility and vendor has in terms of implementing its device or its network equipment. So this is a much tougher thing. I think we can see that from 3GPP, where the kind of for 5G, the first AI features that were how to say, standardized, or maybe they are just still being standardized right now, was really this one-sided kind of algorithms, while this two-sided, for example, CSI reporting, etc., turn out to be much more complex. So at least in the short and medium term, I probably see that AI for communication will be a very important tool, could be a very valuable tool, but probably more in terms of implementation, network implementation or device implementation, and more, not so much specification impact. It may, of course, be reporting, etc., to get the data for the AI learning, etc., but I think it will relatively small in specification impact. One other aspect that's discussed.
Erik,
yes?
Could you wrap up soon?
Okay, I've tried to be quick. One thing we discussed a lot is this integrated communication sensing, which about essentially detecting presence, location, movement of passive objects. What's the point with it? Why this integration? As I see it, the benefit here is that by introducing this as an integrated part of a communication network, reusing infrastructure, spectrum, etc., that we anyway have available for communication, we can introduce sensing functionality with a much lower incremental cost. I think this is a key thing, that it's not have to be exceptionally well operating, it just have to be lower cost. Or it can provide lower cost. And we can use that, of course, to provide new services, or we can use, of course, also use it to enhance the network performance. And there are different levels of this, how much integration. Are we just using the sites, using the spectrum, using hardware, even using waveforms? There are different levels there. I think we will stay somewhere here. We will have reused the same hardware, or using the same waveform. 2 slides left. One other area, mission critical connectivity and dependable networks. I believe that in the future we try to create a network that one can truly trust and depend on, because that's really what will allow us to do a lot of these kind of new service or applications that really, where the user really needs to trust and depend on the network. Could be public networks for automated vehicles, professional video production, etc., or dedicated networks for some industries, manufacturing, within the mining industry, etc. The key thing is really that we have to ensure that we can have truly high service availability. And for that, we have to look into, of course, different type of redundancy alternatives. We also have to provide truly time-critical services. Once again, not exceptionally low latency, but in some sense guaranteed latency. So I think this is actually one of the areas where we can really extend our systems and create, in the end, from our point of view, I mean, new revenues. So today, I mean, we typically mobile broadband. People use our system, quite a large extent, use our systems because it's fun. And that's a good way of getting paid. But another way of getting paid is that you actually provide some services that others can use, so that they instead, in time, makes even more money. And that, I think that is the key thing here. I mean, that if we can get these services, these industries can use our services to make money by themselves, more money by themselves, and then we can kind of get more in general, more revenues into our business. And there's a lot of things we can do on this. I mean, we're discussing use these conditional handover to make it more robust handover, looking to distributed MIMO connected to multiple radio links at the same time to get redundancy. Of course, we need to be able to observe the system. Otherwise, we can't guarantee anything. I mean, if we can't observe how the system behaves, we can't guarantee it, etc., etc. So I think this is important, really important area where we have to ensure that we really end up with something here that is sufficiently reliable, resilient, etc., to really allow for these kind of services. Summary. I think it's good to remember that, I mean, 6G, we're not starting with a blank sheet. It will inherit much from 5G. According to the principle, keep what is good. Why reinvent the wheel? Update if motivated. Be open to that certain things were not done sufficiently well in 5G. Let's go back, redo them somewhat, and make it better. Add if needed. Admit that some things we didn't even think about in 5G. Add those things in 6G. They will probably add it also in the later release of 5G, but that, as I said, they will never be implemented. But in 6G, they will be implemented from the start. And I think it's important here that And I had my first question, something new or more of the same. I think it is to some extent, it is more of the same. It's high data, it's more capacity, etc. But there are new things as well in practice. This dependable communication will be, in practice, it will come with 6G. The truly dependable communication. We will do as good as we can with 5G, but the big steps will really come with 6G, because then we can do it from the start. The situational awareness, which is just a nice name for integrated communication sensing, we are discussing it. It will probably come into 5G in some way, but it will never be implemented. For 6G, it will be there from the start, and I'm quite sure it will be implemented. And it will once again there are new opportunities to provide new services as well as improve our current systems. And I'm just repeating, as I said in the beginning, even if I sounded initially somewhat kind of, how to say, not so, a little bit kind of pessimistic about what 6G should provide. I mean, 6G is definitely critical to ensure the long-term evolution of wireless connectivity, because that's what we've done in every generation has taken us one step further, and not just a step at the when we do the new generation, but it also allows us to continue the evolution within all the generations. So 6G will be really critical to ensure the long-term evolution of wireless connectivity. I mean, we have to do it, otherwise someone else will do it. So that was a little bit what I had to say about 6G. Thank you very much.
Thank you very much, Erik. Very interesting presentation. If you have any question, please post them in the chat. Erik can have a look. And
stop my sharing, maybe.
And we can move on with the agenda. Final presentation by Professor James Buckwalter on high efficiency power amplifiers and transceivers leveraging heterogeneous integration technologies. See your slides, but no audio yet. See the video, but not audio. No, still no audio for me at least.
Hello? Hello?
Oh, now I can hear.
Okay, great. Sorry about that. You can see the slides too, you said?
Yep.
Okay. All right. Good afternoon. Thank you for the invitation to come here. I'm going to talk a little bit about some of the work at a high level we're doing at UCSB on a topic that Erik just presented, talking about how we can integrate sensing into communications in future wireless systems. And then I'm going to dive a little bit more into how I see hardware as part of the differentiation in 6G. And that's some work that I'm doing with a startup company I co-founded that's looking at how to do heterogeneous integration of compound semiconductor devices into silicon. So first, let's talk about how we see the high-level picture of this resilient communications and fusing sensing and communication together to give, essentially our front-end cognitive ability to basically have its own eyes, ears, and even a nervous system that's built around the ability to feedback and control the front end and dynamically change, for instance, features of that front end like sensitivity or power, output power, in a way that allows it to get better idea of what's around the front end, what's around the antenna or the wireless base station. So we're looking at this through the lens of merging in a project called Cognisance, which is sponsored here in the US by the Semiconductor Research Corporation and involves about 30 different faculty. How to bring different technologies together, both at the front end through converging different types of technologies like MIMO radar, LiDAR, with algorithms and with machine learning that might be implemented in very low power ASICs that are used to do feature extraction and provide feedback to the front end elements. So the basic point of this is to ultimately look at how we can tailor energy efficiency for certain tasks in sensing and communication. And this would be aided by adaptation, basically, that allows us to tailor the resources required to perceive a certain object or to do a certain task in the future. My part of this is really the front end, though, and how we might integrate future sensors on CMOS that would enable that combination of communication and sensing. When you look at what we're doing today with MIMO at lower frequencies and think about how we might tailor this to higher millimeter wave bands, we have a large number of antenna elements, and that large number of antenna elements can give us a fairly significant MIMO array that might be used for radar. But we might also bring to bear other technologies that are developing and are becoming lower cost in the future, such as LiDAR, which might be used for sensing or for communications. If we go to an optical type of link that augments what's available from a wireless system. And so combining the optical and the wireless to do sensing through radar and LiDAR might be augmented through a converged sensor, which is both providing a rich set of data that could be used in a machine learning engine or an adaptation, while also being used to support communication. So my interests are really the hardware technologies here, and how do we come up with the low cost, better efficiency devices that are going to enable a much more reconfigurable wireless future. To kind of put this problem into perspective, we can look at the issues in MIMO radar and power consumption required for MIMO radar. It's easy to imagine what happens for one element and where we have a transmitter and receiver sensing a single target. And we can look at the radar range equation shown here on the bottom left as a problem of a near and a far detection. Obviously, to detect something far away, we need a lot of power consumption to transmit a signal and then receive it due to the R⁴ kind of trade space. On the other hand, if we want to detect small, large objects that are nearby, we could imagine how we might tailor the hardware to reduce the power consumption, both by allowing the transmitter to transmit less power, but also allowing the receiver, for instance, to have a lower, a worse noise figure, and save power by being less able to resolve very weak signals. And so by thinking about adaptivity in a radar, we can see one of these ways that we might save power by allowing our hardware, our front end, to trade its power consumption between the receiver and the transmitter in a problem where there might be multiple objects that are in a variety of ranges. And you can kind of come up with the back of the envelope calculation for how many transmitters might be useful and how many receivers might be useful and how that adaptation might be done to optimize power. But it becomes a lot more complicated when you look at a real scene. So we've been looking at how we might leverage a efficient way to build a front end that might join this communication systems, these types of beamforming ideas that came out of the drive towards 5G over the last 20 years, and then merge that with sensing. And so on the left, a traditional RF beamformer would, for instance, be a very linear circuit that allows the transmission of a high order single carrier OFDM signal to the antenna by having linear blocks at each step here. Linear mixer, linear VGA, phase shifter, power amplifier, that's allowing continuous steering of the beam from one direction to another. To imagine how we might move to higher frequency bands and save power at the same time, we're looking at schemes where we might have a constant envelope approach, In other words, the only control is at the phase shifter here and through modulation of the LO in terms of frequency. So we avoid linear PAs. We're going directly from a frequency multiplier through a phase shifter with a constant envelope signal, and only looking at quadrature modulation of each phase shifter across a very large array. And we can use very, very fast switching by bringing digital directly to that phase shifter. We could use very fast switching to both modulate the signal as well as steer the beam. This type of approach actually surprisingly could support not only single carrier, but also the FMCW that's used for radar, or even OFDM that's common in current 5G communications. There are some trade-offs here in terms of quantized control and side lobe suppression. But one of the things we're looking at is as we go to higher frequencies in the millimeter wave space, how we might be able to use the large number of elements, hundreds, thousands of elements, to average this by using very fast modulation on each antenna element. So as an example, just to kind of explain this idea in a little bit more granularity, if you look at, for instance, a 4-channel array where we only use quadrature phase shifting on each of the channels, we can still get beam steering. We can still steer a beam from -30 to 30 in steps. We can also, even with that, without having amplitude control per channel, we can still get a 25-element constellation shown on the right. And if you look at scaling this kind of architecture to a larger array, the ability to sample any kind of beam and any kind of constellation point increases. So there's no limitation really in moving towards large arrays in terms of what signals you can generate. And it's kind of an interesting algorithmic question to figure out how you might control a large array with a limited number of elements per channel. As an example of the kind of hardware limitations, looking at a particular technology like 22 nanometer SOI, we've seen a lot of the silicon technologies, in my mind, reach their kind of optimum levels of efficiency as we've seen scaling of CMOS towards finer nodes. A lot of the technologies that were developed for 5G in the silicon and silicon germanium space are kind of plateauing in terms of the efficiencies they can achieve. So we've shown a lot of work in my group in terms of different device technologies, silicon germanium, but also gallium nitride, indium phosphide, looking at these higher frequency bands and the efficiencies we can reach for front-end elements. And as an example here of what we've done with this 22 nanometer CMOS, even using all the best techniques that we're aware of and power combining, we're plateauing around 20% PAE at 120 gigahertz and around 20 dBm per element. And so that's kind of a way, a guidepost in terms of the type of efficiency we can get when we look at architectures like the one I just showed. We're probably imagining that each element, each channel in the array will ultimately be somewhere between 10 and 20% efficient, but that's going to be a lot better than trying to make a linear channel, a linear array with control of amplitude on each element. We've also looked at how to build TR modules at these higher frequencies in D-band, where antenna spacing is extremely critical for building two-dimensional arrays. We have to keep everything within a very small form factor, 1 millimeter on a side, while we're also contending with the relatively poor RF performance from the standpoint of efficiency. And we've looked at more advanced nodes that are not commercially available yet, but might combine the best SOI technologies like 45 nanometer SOI, which has transistors that have cutoff gain at 400 gigahertz, with 90 nanometer HBTs as well that are at 600 gigahertz. So the transistors have plenty of gain to reach these higher frequency bands. And shown here, you can see the maximum gain that's available with different types of transistor configurations in this process, would easily exceed 15 and 20 dB, all the way up at 140 gigahertz. Also, another interesting note here, the noise figure of these processes is very, very attractive. So comparing this to what we can do with lower frequency millimeter wave bands at 28 gigahertz, these are very, very capable for building high gain circuits at 140 gigahertz. We've been looking at this type of integration in silicon germanium, where we're building TR circuits that have switches, power amplifiers, low noise amplifiers, all within that 1 millimeter by 1 millimeter array tile. And some of the things we found are shown here. We presented this last year. In terms of receive mode, we can get noise figures that are in the 6 dB range, while the efficiency of this circuit's about 10%, including the switch, including all of the losses of the elements. So this is promising, not as good as what we've seen with the 22FDX technologies, but very promising for building more efficient circuits at 140 gigahertz. But it's still not near the efficiency that's available at lower frequency bands. So one of the approaches to moving beyond silicon that we're interested in is something we've been working on at CTTC in terms of heterogeneous integration and bringing different types of device technologies into CMOS. The idea here basically is to figure out how to take the best transistors that are available and look at how to differentiate our hardware technology for the next generation of wireless front ends by bringing different devices to the front end for much lower cost, but also much higher scalability of those devices. So one of the problems today is we all know that there's different types of device technologies that are optimized for different uses. For instance, indium phosphide HEMTs are excellent for low noise. Indium phosphide HBTs are great for getting really high efficiency. They have very high gain. And then gallium nitride HEMTs are excellent for high power. What we'd like to really do in the future is not build everything out of silicon, even though silicon's very low cost, but we'd like to be able to bring these devices into the front end where they're going to make a difference in our hardware performance and give us the ability to build something that has enough, for instance, link power to close the link in millimeter wave bands. So we might want to use, for instance, the indium phosphide HEMT in the receiver. We might want to use a gallium nitride HEMT in the power amplifier while keeping the rest of the circuit in largely a silicon process. So the idea here basically is to combine any kind of technology, which we're denoting as X, with CMOS, while achieving something that mimics the silicon cost and scalability that the ecosystem for commercial devices is going to demand. The way we're doing this basically is to leverage the existing ecosystem of compound semiconductor devices that are made on 4-inch or even 6-inch wafers, and combining that with the existing ecosystem of silicon devices that are made on the 8-inch or 12-inch wafers. Those larger wafer diameters give silicon a great cost advantage, while the smaller wafer sizes in the compound semiconductor generally are what drive it towards a much higher cost model that makes it difficult to bring into commercial devices outside of the base station or the PA and handset. What we end up doing is just using the compound semiconductor for making transistors. No matching elements, no large inductors or transmission lines. We just use it for building transistors, just getting transistors out of it, much like the ones that I showed here. These are just transistors that are integrated into what we call chiplets. And those chiplets can then be put into the silicon wafer in cavities. You can see here an example of a silicon coupon where there's cavities that are so small, they're just these little black dots in the cavity. And what we're trying to do is basically use an assembly technique to put all of the different chiplets that we desire into those cavities, and then build what we call a reconstructed silicon wafer that has this 35 material in it. There's a lot of advantages to this. One is, of course, we're more and more worried about the supply chain around compound semiconductors. And so this doesn't waste as much compound semiconductor material because we're only using it for the transistor itself. The other thing we're able to do now is we're able to allow a more rapid transition of a new device technology into a commercial system. We don't need to wait 5 to 10 years for that device technology to migrate to a level of qualification that allows it to be considered as part of a commercial ecosystem. We instead can bring that much more quickly because they don't need to develop the back end of the line structures. They're going to be part of the silicon design. Additionally, it helps us reduce the costs because we're using the entire wafer just to get transistors. So the amount of area that's used for each device is relatively small, and it makes it compatible with CMOS for controlling that device and biasing it and allowing power management to all be done in an integrated platform. So as an example of what we've demonstrated, this was actually presented last year at the RFIC conference. We showed how we could use 2 different technologies, indium phosphide on the left to get very high efficiency in the kind of traditional FR2 bands, lower millimeter wave, and get more than 35% PAE from this amplifier. While on the right, we're showing a gallium nitride HEMT that's integrated into this platform, where we're getting about 7.7 dB of gain at 28 gigahertz. While being biased at 20 volts. And you can see in both of these examples, we're integrating a chiplet here, which is just the transistor, but then doing a wafer scale interconnect that allows all of the matching elements on that circuit to be in silicon. And so this opens a door for us to add a lot more silicon functionality into future front ends. Some of the things we're looking at now involve combining different types of device technologies on a silicon platform. We're using indium phosphide HBTs, for instance, to drive gallium nitride HEMTs in what would be a more efficient and linear transmit chain on the left. And then on the right, we're looking at building TRs, transmit receive modules that might be available for integration into future handsets or into base stations around the same 28 gigahertz hardware I showed in the last slide. So these types of demonstrations could include switches that are in different technologies than the power amplifier, while we're using indium phosphide HEMT in a low noise receive path. Well, we're developing this technology now up at higher frequency bands like E bands that were mentioned as part of a portfolio of bands that might be used ultimately as in 6G for backhaul, as well as for some of the sensing and communications we talked about earlier. We see this as being a much better approach ultimately than just using silicon, while also outperforming potentially gallium arsenide in terms of RF performance. So in summary, I'd like to just share a couple outlooks. I personally am a circuit designer, very different than some of the other talks today, but I see hardware, and what I'd like you to take away is that I see hardware as part of the 6G differentiation. There's going to be new device technologies. We're going to, I think, move beyond CMOS and silicon germanium. They're great for making these multifunction arrays where we might integrate sensing and communications together, as I described at the beginning of this talk. And they're great for getting higher frequency bands like D band, as I demonstrated as well. But we're kind of seeing a plateau in what we can get in terms of efficiency from these technologies. And so the part of the message today is I'm really optimistic that bringing other types of devices into low-cost platforms will help us get higher efficiency and really push the capabilities of hardware platform to meet some of the needs of communication systems in the future. And the final message is I really see digital at the antenna on large scales as an exciting approach to allow us to get some of the multifunction that we like, integrating sensing and communication together. And so we're really looking both from a university perspective at these types of systems, while at CTTC trying to figure out how we build low-cost wafer scale integration techniques that allow us to assemble a next generation of front-end technologies. So with that, just acknowledge our sponsors for this work, and yeah, happy to take questions.
Thank you very much, James. In the chat, I think the questions are for previous speaker.
Okay.
Looking at the agenda, the next agenda item is open discussion and questions. So if there's any question for James or any of the speakers. It's all clear from everyone. So any questions to any of the speakers in this session or from previous sessions that's still in here? Mitch, take the opportunity now.
Yeah, thank you, Patrick. Yeah, thank you for all the presenters provided very interesting insights for this session. And actually, I think in particular, I have some question. Maybe I want to see if Erik can also help enlighten us. There's Erik, you're talking about is that 6G is critical to ensure the long-term evolution of wireless connectivity. Right, I agree with this statement. However, if we look at the wireless history, there are 2G, 3G, 3G to 4G, and 4G, and each stage we have some wow factors, some great things to help the operators to either improve the network efficiency or to increase the capacity, which kind of align with the wireless network operators' goal. But unfortunately, my observation is that that seems to have a breakage in this 4G, 5G transition, right? And then, and of course, I cannot be blamed for that because I stopped at the LTE, CDMA interworking, then I went to work on IoT. So those guys in 5G, that seems like I say we have a lot of use case proposals on that, and I didn't learn at that when in the 5G era. But when I came back to 6G and I start repeating those use cases, then immediately people are asking me that, hey, Mitch, those use cases you're talking about has been discussed in the 5G, right? So with that, maybe this is a good time, Erik, see if anybody here say, should we kind of start thinking about how we try to avoid repeat ourselves? So before we migrate to 6G, we probably also need to focus on how we can use the 6G, how we can have this usage in the 6G rather than just focus on technology driven. So, Erik, thank you.
I mean, on the first question, when I said that 6G is critical for the long-term evolution, that was really kind of more directly related to this fact that I said that even if, as we go from, let's say, take it kind of go one step back for say, when we went from 4G to 5G, the first release of 5G was probably not very much better than the kind of simultaneously coming 4G release. But by having a new generation, we kind of open up that new generation could then continue to evolve in a way that the LTE would not have been continued to evolve. So that's what really I meant. That I mean, if we don't get any new generations, we will continue to evolve what we have, but that evolution will kind of flatten out quite quickly. That's what more directly said. Then I'm not sure exactly what you said about new use cases for 6G? I fully agree that what people said for 6G quite a lot resembles what people said for 5G. And even I sometimes look on my slides for 4G, and actually those slides also look a little bit the same in kind of what we're going to achieve. At the same time, I think it's quite clear we in practice we have achieved quite a lot. Things getting better all the time.
Yep.
I'm sometimes at the same time, sometimes kind of, I mean, I don't want to emphasize the new generation. It's not so that just because we have a new generation, we get the dramatic improvements in things or get a completely new kind of use cases supported. But I mean, they will always be a little bit better. And in some sense, we could see even the generational steps are a kind of just a little bit bigger steps on the general evolution path, which of course, at the same time, makes it very important that the cost for the operator to go to a new generation. I just realized I don't have my camera. The cost for the operator to go to a new generation must not be very big. I mean, it's exceptionally important that we can get the cost to go from like 5G to 6G should essentially not be very much more expensive than to go from 5G release 20 to 5G release 21.
Well, one related element is also that it has been said that the even generations are like correcting something that was in the odd generations. So let's see how much that will apply then to 6G and 5G. But some of these things require to become fully available and fully established. They require even a kind of beyond a generation development so that you can learn from the previous generation.
Yeah, but actually, my question is not like I said, we need a more new 6G use cases. That's not what I meant, because I think Andreas Müller from 5G ACIA already pointed out that say all the 5G use cases are still valid for 6G, right? We already learned that. But my viewpoint is mostly like yes, we do want to have a technology evolution, but when we were evolving the new technology, we probably also need to spend more time and then think about how these technologies can be applied and used by the users, right? Users, not necessarily just individual users, but also all the targeted verticals and those parts. So that's what I meant. Thank you.
Yeah, thanks. Yeah.
Kuntal.
Yeah, so this question is for James. So I was trying to follow your presentation. So in the case of radar processing for MIMO radars and beamforming radars, there are already silicons available in the market for, say, E-band, for mostly used for automotive. Can we leverage something from that, the radar industry already?
Yeah,
do you have to build something brand new?
That's right. We're certainly looking at what's been done on the market already. What we're focused on in the project is looking at 140. So you only get a kind of modest increase in the number of elements that you can integrate when you go from 70 to 140, right? 4 times the number of elements. But we're adding new features into that type of radar architecture where you have the quadrature phase shifting. And then we're using the quadrature phase shifting to do really, really fast phase control. So, the parts that are on the market today, they don't have phase shifters that let you switch at, say, 10 gigahertz sample rates. And so we're looking at very, very fast control of the phase shifters to allow you to shape the beam, to interpolate between different phase elements so that you get something that's more continuous than you might find in a kind of automotive radar front end. And then ultimately, it should look like an automotive front end in some modes of operation, but then it should have some additional features that are hardware related that are going to allow it to do communications, right?
Thank you. For one quick question. I saw that in your presentation you mentioned something about the MIMO and beamforming fast switching. Is that because we are trying to estimate the range of the objects that are far away from the base station, or also close to the base station at the same time?
That's right. We'd like to support both beamforming and MIMO, and so you might have MIMO modes of operation where only a few transmitters are turned on. That would resemble what a current automotive radar does, right? It doesn't use a large number of transmit elements that are a lambda over 2. There's a few elements that might be several lambda apart, right? But you could also imagine modes of operation where you need to see far, that you'd want to use something like a transmit beamformer. And so if you have the hardware there, you can turn on those elements and form beams in certain directions and augment your ability to detect something that's farther away under a low duty cycle kind of short duration, right? So that you don't consume lots of power all the time. You just do it to see what's out there and then move back to a different mode of operation. Does that make sense?
Yeah, it makes sense. Just last question on that. So are we envisioning two separate RF front end then? One for comms, one for sensing?
No, I'm hoping that it's, well, the research at the university is certainly focused on using a single front end to do it, right? So it's repurposing by making each channel simpler and relying on fast digital switching. We're trying to use the same front end, the same aperture for both the communications and the sensing.
Great. I can probably contact you offline to discuss some more on this topic.
Yeah, sure.
Yeah, and quickly, part of my ignorance, like today, we actually have two presenters, Professor Okada and also Jim. Actually, you lock into this D band.
Yeah.
The D band, yeah. I really haven't really invested much on that one. So is the reason that you bring this up mainly because like a LiDAR and those usage for automotive, or you have other applications area in mind for using D band? Thank you.
I'd say from my perspective, this is something that's largely driven by funding agencies, right? They, we have to look differentiated from what's commercially available in E-band. There's knowledge in trying to apply technologies at higher frequency bands. My hope is that, the ideas, the circuit concepts can be translated commercially at lower frequency bands later on. But we're certainly aware that I think using 140 gigahertz commercially is a long way off, right? I'll probably be retired.
Thank you.
Do you have time for some more discussion or no? Sorry.
I do.
Okay, so thank you. So then the question for Chen Tao, I think the discussion on SBA for RAN, I had many comments. The question is that, the service mesh and the sidecar is not real time. If you implement microservices in a container cloud-native infrastructure, it's not real time at all. So implementing service mesh or SBA for RAN has been a big challenge. So is there sort of like a open source project in CNCF that we will start to make that happen? This is for, I think, Chen Tao, that VTT discussion. Maybe he's not there.
Still in the participants list, but seems not.
Okay, since not there, I can go to see if I can ask one more question to Erik.
Yes.
So Erik, I think the comment that I had about pilot pre-operation in physical layer,
yeah,
which will require a new waveform because 5G waveforms do have pilots. So. Yeah. Are we sort of closing the door on exploring new waveforms or new way of doing things in physical layer in 6G?
Let's say like this. I mean, first we have to be aware of that. In some sense, we are quite soon closing the door on any of the fundamental features of 6G because standardization will start quite soon, and at least. When I listen to my colleagues in the industry, I mean, it seems very much that we are arriving at something which is kind of very similar to what we have today in terms of now I'm basic waveform, like when I talk about OFDM. Then I guess you are more into this kind of think about different specific constellation modulation constellations, for example. That I think we could consider as some kind of extension, because as I said, one important thing of the waveform is that we need to really ensure that we have the compatibility with the 5G waveform for this kind of spectrum overlay. I would assume that this constellation, more advanced constellations, would still fall under that constraint. So that would kind of, you could have that still overlaid. So that can definitely be considered. Then we had to have this about having specific constellations to get kind of a reduced pilot overhead, etc. As I said, we have looked into it. I still don't believe that the gains are that big, but of course, if someone can show that the gains are substantial, we should consider it. Absolutely.
Great. I mean, if any of you will be at the MWC coming up, there will be a demonstration on that from AI down the lines, pilot-free operation and constellation shaping on a site-specific basis based on AI/ML. There is promise, but of course, there are claims that we haven't really actually tested, but there are some claims. So we can see, and since 6G's early days of 6G development, there could be some more adaptation, as you said, without breaking the backwards compatibility with 5G.
Yeah. And I mean, I'm at research. I mean, I'm always happy about new advanced things. I'm quite sure that my colleagues down that are closer to the product development, they're always slightly less inclined to embrace completely new things.
Absolutely.
Yeah.
Which is always a quandary.
Yeah. And Mikko and Patrick, nice to meet you again. Thank you very much for organizing this workshop. I guess through these 2 days, I did see a lot of very interesting presentations. And then I also tip my caps to our colleagues in Hexa-X-II. You guys are working very hard. And then I appreciate all your effort on this one, and understand that there are some publications coming up pretty soon. So I'm looking forward to seeing those. And especially Mikko, yesterday, we have a series of 3 presentations talking about this, using this network function in a very interesting way, like almost like my interpretation is that you also want to drive to like a verticals by using a network functions to have this vertical support. And those are very interesting concept for me, because as you know, that I'm actually looking into these applications, right? So I like to see more into those parts, and then I understand that can be a basis for like a very intelligent core network or core support for all the applications. So I'm looking forward to seeing those parts. Thank you.
Thank you, Mitch, for the very active contribution and participation.
Thank you, Mikko and Patrick, for this fantastic workshop. We learned a lot, and looks like I echo what Mitch said. So I look forward to engaging more and see what we can do together.
Yeah. And Kunto, it's good to see you here.
Yeah. Thanks.
Yeah.
Thank you.
Thank you.
Thank you.
So thank you to all the speakers, and thanks a lot to all the audience. It's been very interesting presentations and interesting discussions. As mentioned before, the presentations and recordings will be uploaded to the Hexa-X-II website if the presenters give permission. And with that, I think we can close the workshop. So thank you all.
Thank you all.
Thank you.
Cheers. Bye.
Bye, y'all.